Okay, before we talk about inverse matrices, we have to talk about that other I word, the identity matrix. So here we have identity matrices, or the singular matrix, and they're very special matrices. They're always square. They're only filled with ones and zeros. So if, for example, if I had the 2 by 2 identity matrix, I'm going to call it I subscript 2, and it goes 1, 0, and then 0, 1. Let me throw you another one. If I had a 3 by 3 identity matrix, I would call it 1, 0, 0, 0, 1, 0, 0, 0, 1. And you'll quickly notice as I write more of these out that there's always ones on that forward diagonal. Okay, so notice that along this diagonal is the ones and everything else is 0. So this is a special matrix and we call it the identity matrix. What makes it so special is that there's this rule that says the identity times any matrix, so make sure it's the correct size to multiply it, so choose which identity would be the right size, and you just get back to A. Okay, so it's kind of like multiplying a number by 1, you get back to the number you started with. The same thing here, if I multiply a matrix by I, the identity matrix, then you get the same matrix that you started with. So, but it's also true that I can do it in both directions. A times I would also equal A. So let's make up a matrix A. So let me say A is equal to 4, 3, 5, and 6. Okay, and let's see what happens when I take that times A. So let's do A times I first. Would be 4, 3, 5, 6 times the 2 by 2, 1, 0, 0, 1. And let's see what happens when I multiply those together. I'm going to use the first row with the first column. And that will give me this first row, first column here. Maybe I should have done that in yellow. So 4 times 1, right, is 4, plus 3 times 0 is 0. So 4 plus 0, I'm going to put a 4 there. Okay? Then I want to try using the first row with the second column, and that's going to go here. So the first row, 4 times 0, 0, and then the 3 times the 1 is 3. Adding those together, I get 0 plus 3, 3. Okay? Let's do another one. If I take the second row with the first column, that means I'll be here, right? Multiplying each pair, the 5 times the 1 gives me 5, and then the 6 times the 0 gives me 0, so I have 5 goes here. And finally, I'll pick my last color. Yeah, I think you see what's going on here. Oops, let's try pink. If I take the second row with the second column, my answer is going to be here. You can come in. Do you want to be in my... Hi, Vicki. What's up? How are you doing?
Good.
All right. Okay, so we're working on the pink one, right? Second row, second column. 5 times 0 is 0. And then I need 6 times 1 is 6. I add those together and get 6. So look, I've got this new matrix, the 4, 3, 5, 6, identical to the matrix that I started with. Okay, so that worked, and I'll leave it as an exercise to the viewer to take the next step on all of this would be I times A, and see if you get the same thing as well, okay? And it should work out that you get the identical matrix. So again, this is another way to practice your multiplication. Okay, today we're going to talk about the inverse of a matrix. So let's define what an inverse is. If you have a matrix A, then its inverse can be notated A inverse, just like we had F inverse for functions. This is an inverse matrix A. So that's the inverse of matrix A if it's true that A inverse times A is equal to that identity matrix. And you can go both ways, of course. A times A inverse is also equal to the identity matrix. So as you can see, A must be square, okay, so in order to be able to multiply it both ways. And its inverse will then necessarily be square as well. So we're going to do, the first thing we're going to do is just prove that given these two matrices, are they inverse of one another? So let's start with A is equal to -1, 2, -1, 1. And let's have B is equal to 1, -2, 1, -1. And let's see if I multiply these together, do I get the identity matrix? So if I take, let's see if I try this. A times 1, -2, 1, -1. What will I get? I'll do matrix multiplication, first row, first column. So that's -1 plus 2 here. And then first row, second column this way. Then I have -1 times -2 is 2 plus this 2 and this -1 minus 2. And then I can take second row, first column, and get -1 plus 1. And let's see here. If I do second row, second column, I've got 2 plus a -1, which all is said and done, I'll reduce everything 1, 0, 0, 1. And indeed, that's the identity matrix, so that worked out. And then I would just do it again the other way, take B times A. Okay, now there's ways to do this with an augmented matrix and row operations, but I just want to save a little time, and we're going to go straight to the inverse of a 2 by 2. Okay. We've done enough with row operations. I think let's save some time and move through this section more speedily. So just as an example, the 2 by 2 is a special case, and things work out nicely for it. So it's nice to have a handy formula for a small 2 by 2 matrix. And it goes like this. If you have a matrix A, and let's label simply A, B, C, D. So A, B across the row, then C, D across the second row. And as long as, an inverse exists, because, oh yeah, I forgot to mention, not every matrix will even have an inverse. So we'll see what happens when this one doesn't. But the A inverse will be given by this formula. You do 1 over AD minus BC times the matrix. What you do is it's D and A. So let me just show that. These two terms right here have just switched places, okay? And then the other two terms pick up a negative sign. So minus B and minus C. Okay? So it's more of a process than a formula to remember. Switch these two, add the negatives to the other diagonal pieces. Alright, so that's the formula. You can see you're not going to have an inverse when this AD minus BC term right here is equal to 0. So in that case, then there will be no inverse. So let's do an example. If A is 3, -1, -2, and 2, let's find the inverse by the formula. 1 over A times D minus B times C. And these are all, everything's working on diagonal here. -1 times -2. So be careful of all your negative signs. times the matrix. I'm going to switch the diagonals that go this way, and I'm going to add negative signs to the others so negatives turn into positives. And let me clean it up a little bit. 1 over 6 minus 2, 4. 2, 1, 2, 3. So this is 1/2, 1/4, 1/2, 3/4 is A inverse. So let's let you try one on the next page. What if I had B was equal to 3 minus 1, negative 6 and 2? Find B inverse. I'm going to pause it and see if we have the same answers. Alright, so kind of a little letdown. I found that B inverse does not even exist. So why do we care about having it inverse? And the reason is very simple. For the most part, we like them for solving these systems of linear equations. In a system of linear equations, let's say, okay, we have this system of equations. We could write this in matrix form, find that coefficient matrix, 1, negative 2, 2, negative 3. And if I multiply that 2 by 2 by the variable matrix, x, y, I'll get this 5, 10 matrix on the right-hand side. So what we've got is a matrix equation AX equals B, okay, or X is a capital letter standing for that XY matrix. And you should probably go ahead and do the matrix multiplication and convince yourself that this is true. You know, first row here times this column will give you 1x plus negative 2y equals 5. Okay, so kind of work that out in your mind. So we have this matrix equation, and I want to be able to solve this. Now, one thing we never learned how to do was dividing matrices. So if I had looked at this in the land of algebra, I would have just divided by A and found x that way. But I can't do that with matrices. So what do? Well, this is where the inverse comes in. I'm going to multiply both sides of my equation by A inverse on the left. Okay, remember, matrix multiplication is not commutative. Okay, so if I'm doing it on the left side of the equation, I have to multiply on the left for the right side of the equation too. Let me show you. So this is A inverse A times x is equal to A inverse times B. Okay, and I choose to associate this way, so I have I x is equal to A inverse B, or just x, because that is identity matrix, A inverse B. So there you have it. This is exactly why we want inverse matrices, because if I have this matrix equation, I can solve it using this for x, the inverse. So let's go ahead and find A inverse. I knew A was the 1, 2, 2, negative 3 right here. That's A. So A inverse will simply be 1 over the AD, which is negative 3, minus BC, which is negative 4, times the matrix. I'm going to switch positions, the negative 3 and the 1 on that diagonal switch positions. The other diagonal simply adds a negative sign, so that becomes 2, and that becomes negative 2. So what do we have? In the front, that scalar is just 1 over 1, or just a 1, so I can drop it. So I know A inverse is negative 3, 2, negative 2, 1. There's A inverse, so I'm going to solve for x. X is equal to A inverse B, so negative 3, 2, negative 2, 1, times the B matrix, which was the 5 and the 10. So let me do this matrix multiplication, first row, first column. Negative 3 times 5, negative 15, plus 2 times 10, 20. Okay? And then I got second row, first column, negative 10 plus 10. Aha. So that comes out to be 5, 0 for my X matrix. So that means X, little x, is 5, and little y is 0. And that's my solution. All right, let's let you try one. I want you to solve this system of equations. The first thing I want you to do is write this as matrices, okay? Then you'll need to find the inverse of the coefficient matrix and work out the solution from there. See if you can do it. And my solution, x is 19, y is 15, and it does check out. So see you in class, and I'll show you an even better way to do larger matrix equations on your calculator.